Now let us derive Euler's equation of motion. Okay, so in this motion equation of motion, only forces due to gravity and pressure are taken into consideration. Okay, now just consider this streamline over here. Now this is one streamline here in which the flow is taking place with pressure P and in the direction of S. So in the direction of S, this is one streamline. Okay, now consider a cylindrical element here. Now this is one cylindrical element of cross section. This cross section is dA, the cross section of this, and of length ds. Okay, now here the pressure force that are acting in this particular direction, the force that is acting here in this direction is stay given as P into dA. Now there is one more pressure force that is acting in this particular direction, so that will be P plus dou P by dou S into ds into dA. So you can consider this sections as dou P by dou S. So this into this whole section is an additional force into dA. So this is one pressure force that is acting. Now this line over here, it is nothing but the weight of the element. Now the whole weight of this element, it can be written as rho g into dA into ds. Okay, now this is the weight of the element. Now let us write this down, all these forces. So the first force will be pressure force now this particular force in the direction of force, so that is nothing but P into dA. So this is one force. Then the second force that is acting here is pressure force in opposite direction. That is nothing but P force, of course the pressure force, plus the additional forces is nothing but dou S by dou S is all the partial differential of this particular section, that is dou P by dou S into ds, the length ds, the whole thing into dA. Okay, now the third force that is acting here is nothing but weight of the element. That can be written as rho g dA ds. Okay, now let us take this theta. Okay, now let us take this theta is the angle between the direction of flow and line of action of the weight of the element. Now this is line of action of weight of element and this is the direction of flow here. Now I'll just write down one equation, that is the resultant forces, or the resultant forces is now this is acting in this direction, you need to, I'll just write it down. So this is d theta, this is ds, and you'll write this as dz. Okay, and this is adjacent here. Now the resultant forces that are acting along the line of action, it will be written as P dA minus opposite force that is acting P plus dou P by dou S into ds into dA minus rho g dA ds cos theta. So take this as equation 1. So this is the force, okay, resultant forces. Okay, now next mass into acceleration. Mass into acceleration is, okay, of this will be rho ds dA into as. Okay, now this is nothing but the mass in s direction, and this is the acceleration. Sorry, write it as. Okay, so in this as, where this as, it's not a, sorry, a small s is equal to dv by dt. So it is a function basically dv by dt, where in this v, this particular v is a function of, it is a function of s, that is displacement or the distance you can say, and time. So you can write this particular equation as, so you can write this dv by dt can be written as dou v, as a function of s and t, it can be written as dou v by dou s into ds by dt plus dou v by dou t. Okay, so this is equation 3 here. So this is first equation, this is the second equation, sorry, I didn't mark it. Second equation, this is equation 3. Now we know that change in displacement by time, or displacement by time, not change in displacement, sorry, displacement by time is nothing but velocity. So you can write it as ds by dt is equal to v. And for a steady flow, dv by dt is equal to 0. Okay, so when this is equal to 0, we can write this particular equation as v dou v by dou s, okay, v is substituted, plus 0. So as is nothing but v dou v by dou s. So this equation you can consider to be equation 4. Now substitute this thing, this as, in the equation 2 and 1. So equating 1 and 2 and then substituting this equation in the equation 2, what we get here is, so equating equation 1, I'll write the whole equation now, that is p dA, yeah, I can write it down, minus p dA minus dou p by dou s into ds minus rho g dA ds cos theta, that is equal to, since we know that f is equal to ma, so that is equal to the mass acceleration rho ds dA into v dv by ds. Okay, now this is the whole equation where these things cancels out. And now what we need to do is divide this whole equation by, divide it by rho ds into dA. So when we divide this particular equation, what we'll get is yeah, dou p by excuse me, sorry, I missed out on dA over here. So dou p by dou s into dA by ds divided by rho ds into dA, cancels out, minus here, even same here, rho g dA ds cancels out, cos theta, that is equal to rho v dv by ds. Oh sorry, it is rho this thing, right? So even rho cancels out. Okay, so we can write this equation, we can write this particular equation as, you bring this to the other side, then what we can write this equation as is minus dou p by rho ds, or dou s, sorry, dou s plus g cos theta plus v dv by ds, that is equal to 0. Okay, now here we know that sorry, this is theta, so this is ds, so cos theta is nothing but dz by ds. Okay, so substitute that by dz by ds. So what will write the final equation to be as 1 by rho, not this minus sign here, dou p by dou s plus g dz by ds plus v dou v by dou s. So this is equal to 0. Okay, or you can write this as this equation, sorry if it's not visible, yeah, you can write this particular equation as, since ds is a denominator, you can even write this equation as dou p by rho plus g dz plus v dou v is equal to 0. So this is the Euler's equation of motion. Okay, so this is the equation, Euler's equation of motion.